I'm going to walk you through how to calculate the internal member forces for our truss example here. So we already calculated the reaction forces. Now we're going to calculate those internal member forces. So the first thing we're going to do is we're going to label our diagram here, our free body diagram. So I'll label this point A, this is point B, and this is point C. And we'll go ahead and put in the forces that we already know are acting on the system. So right here we have 100 magnitude force, and I'll label that as F. We have a reaction force at point A in the Y direction, and we calculated that on the last example as 30 pounds. So I'm going to go ahead and label that as 30 pounds. And we also have a reaction force at point A in the X direction. And because there were no forces in the X direction, that is 0 pounds. Alright. We also have a reaction force at point C in the Y direction. Because it's a roller connection, it only has one direction of support. And we calculated that when we did our reaction forces as 70 pounds. Alright, now we're going to be calculating, if we put this 100 magnitude force on our truss here, what does member AB, what happens to member AB, what happens to member BC, and what happens to member AC? So the next thing we'll do is what I've done is I've created a free body diagram here for just this point, so we can look at it a little bit more closely. And so the first thing I'm going to do is come over here and we're going to label some of these same things. And so right here we have a pin connection, and we know this is 30 pounds, but I'm going to label it as the variable now. The reaction force at A in the Y direction. Here we have the reaction force at A in the X direction. We know that this is member AB, and we know that this is member AC. All right. Now to calculate the force on member AB, we have to do some vector addition. And so I'm going to go ahead and I'm going to draw up a vector in the Y direction, and I'm going to draw over a vector in the X direction. And so we're going to label this vector A, B in the Y direction, and this will be the magnitude of A, B in the X direction. And so once we find these two, we can figure out the force on this member. Alright, so the first thing we're going to do is we're going to calculate ABX. So I'm going to write that right here. The force of member AB in the X direction. That's what we're calculating. Alright, if we look at this triangle right here, we have 45 degrees here, but we're calculating this one. And so we know that this is a 90-degree angle, and so this angle right here is also 45 degrees. And I'll go ahead and write that in. Alright, so the first thing that we're going to do is figure out which function to use. In this case, we are going to use the sine function. And so I'll say the sine of theta is equal to the opposite over the hypotenuse. Okay. Now we'll substitute the sine. What's our angle? It's 45 degrees. So the sine of 45 degrees is equal to the opposite, which in this case is ABX over the hypotenuse, which is AB. All right, so we're just putting in variables now. And so then we can do our algebra and get ABX by itself. So ABX, the magnitude of member AB in the x direction, is equal to the sine of 45 degrees times member AB. Okay, and so that is AB in the x direction. And again, we just have variables now. The next thing that we'll need to calculate is ABY. And so here we're going to calculate member AB in the y direction. So I'll do that in the y direction here with cosine. So the cosine of theta is equal to the adjacent over the hypotenuse. Substitute the cosine of 45 degrees is equal to the adjacent, which is ABY, over the hypotenuse, which is AB. We'll do algebra to get ABY by itself. So ABY is equal to the cosine 45 degrees times AB. So once we have those two things, we can go ahead and solve for member AB. So I'll just go ahead and right now we're going to solve for AB. And we're going to do that with our static equilibrium equation. And so if we sum the forces in the y direction, they have to equal 0 for static equilibrium. So now we'll just go ahead and add up our forces in the y direction. So the first force we have is the reaction force at A in the y direction. We'll add that to the next force we have. Here we go. We have AB in the y direction, member AB in the y direction. And those two things have to equal 0. All right. So now I can go ahead and plug in my numbers. I know RAY. We've already solved for it. It's 30 pounds. Plus ABY, which we solved for right here. I'll go ahead and circle that. So we remember this is the answer. Plus the cosine of 45 degrees times AB. Okay. All of that has to equal 0. And so now we need to get AB by itself. So I can subtract the 30 pounds from either side, and I get the cosine of 45 degrees times AB is equal to negative 30 pounds. I can then divide both sides by the cosine of 45 degrees, and I get AB is equal to negative 30 pounds divided by the cosine of 45 degrees. All I have to do then is calculate. So I will take 30 negative divided by 45 cosine, and I get negative 42 AB is equal to negative 42.43 pounds. And I'll go ahead and circle that. So what that tells us is that member AB right here on our system has a force of 42.43 pounds on it, and we know that that force is compression because it's a negative number. So that negative number gives us direction. Alright, so the next thing we'll go ahead and calculate, since we have member AB calculated, we'll go ahead and calculate member AC. And so, again, we're going to solve for member AC. And so I'll go ahead and write that. Solve for AC. Okay, so again, to solve for AC, all we need to do is we need to sum the forces in the x direction, and they have to equal 0. So our forces in the x direction are, if we look at our system over here, the reaction force at A in the x direction plus ABX, member AB in the x direction, plus member AC. Those have to equal 0. Okay. We know RAX is nothing, so we'll just leave that blank and we'll plug in ABX. So here we have what ABX is. ABX is equal to the sine of 45 degrees times member AB. We have member AC to add to that. And all of that has to equal 0. We can now plug in what we know member AB is. So again, I'll use the sine of 45 degrees times member AB, which we calculated down here, was negative 42.43 pounds. We'll add AC to that, and all of that has to equal 0. Alright, so we'll do our algebra. Turn our number around, we'll get AC by itself equals the negative sine of 45 degrees times negative 42.43 pounds. And I'll go ahead and calculate on my calculator. So I'm going to say 45 negative sine times 42.43 negative. And I get member AC is equal to 30.0 pounds. Remember, AC is a positive number, and so that we know that that member is in tension. So I'm going to put our arrows facing out, and I'll write in 30 pounds.